All right, so here we're going to start chapter 7. And what we're going to do is we're going to talk about eigenvalues and eigenvectors. I want to describe this in a general linear transformation first, and then we'll apply this to a specific type of linear transformation, namely matrices. So what we're going to do is we're going to start, let's let T be a linear transformation from a vector space V to itself. Let's suppose that V has dimension n. And what we're going to do is we're going to say that the value lambda is an eigenvalue of T if there exists a non-zero vector. So if there exists a non-zero vector x such that T of x is equal to lambda x. Here x is called an eigenvector. We insist that x is non-zero because we know that for any linear transformation, the zero vector gets mapped to itself. So we're not allowing that possibility to determine an eigenvalue. Hence, that's why we insist that there's a non-zero vector x with this property. I want to note that if x is an eigenvector for lambda, under some linear transformation T, then so is any multiple of x. So Cx is also an eigenvector for lambda. For any real number C. And the reason for this is pretty straightforward. It has to do with the definition of a linear transformation. Note that I should start by saying that if x is an eigenvector for lambda, this means that T of x is lambda x. So let's compute what's T of Cx. Well, I know that I could bring the C outside, and I know that T of x is lambda x. And so then I can rearrange the lambda. This is a lambda. So then I can rearrange the lambda to be lambda times Cx. And so what happens is you have T of Cx is equal to lambda times Cx. And that tells you that Cx is also going to be an eigenvector for lambda. So eigenvectors are far from unique. So if x is an eigenvector, so is any constant multiple, any scaled version of that vector will also be an eigenvector. One other notion that's going to be really common for us or really important for us to study is what's called an Eigen Space. So we're going to describe E sub lambda. And what this is going to be is it's going to be the set of vectors x such that T of x is equal to lambda x. So this is going to be what's called the Eigen Space, the set of vectors that satisfy. It's going to be the set of eigenvectors for the eigenvalue lambda. It turns out that E sub lambda is called an Eigen Space. I should just say that. Is the Eigen Space for the eigenvalue lambda. And the reason why we use the word space is that it turns out that E sub lambda is a subspace of V. I'll let you prove that on your own. It's super straightforward because of the properties of a linear transformation. So that's the eigenvalue, eigenvector, and eigenspace, which are the big ideas, the big things to talk about in this chapter. So what we're going to do next is we're going to specifically focus in on, we're going to study this, we're going to focus on a specific linear transformation, and that linear transformation is going to be the transformation from Rn to Rn given by T of x is AX. Here A is an n by n matrix. It's square. So it has the same number of rows and columns. In this case, we're calling that n. Notice that I'm using n slightly differently here. Okay, so here n was the dimension. Here the dimension is n squared. Anyways, so what we're going to do is we're going to study eigenvalues and eigenvectors for So we're going to study eigenvalues and eigenvectors for these linear transformations. And what we're going to do is I want to kind of describe this process, how we're going to go through it, how we're going to find them, and then we'll do some examples. So what I want to do is I want to solve, remember we're looking at t of x equals lambda x, and our t of x here is ax. And this is a little bit different. Notice that we have a vector x that we're acting on in two different ways. This vector here, ax, is a matrix product. It's the matrix A times the vector x. And this is just a scaled version of x. So all we're doing is we're taking the vector x and multiplying all the quantities by lambda. I think it's actually very helpful in this case to think of both of these as matrix products. And the matrix that we have to multiply on the right is lambda times the identity matrix times x. Of course, I can just add in this identity matrix for free because I know, because it's the identity matrix, anything I multiply by the identity is itself, as long as that product is defined. So I need I to be on the left in order for, because this I is an n by n matrix, x is an n by 1 vector. But as long as that product is defined, those are equal. And so what we're really looking for is we're really trying to find what are the solutions to ax. Let me write this one more way before I get to what I want to say. But what are the solutions to ax minus lambda ix equals 0? Here this is the 0 vector in Rn, so 0, 0, 0, right? And really I want to think about what are the solutions to a minus lambda I times x equals 0. So for what values of lambda are we going to have solutions to this? And I want you to remember what we know about matrices, and we know quite a lot now. So we know, for example, just as an aside, we know that b of x equals 0 always has at least one solution, namely the 0 vector. And if bx equals 0 has infinitely many solutions, so if this has infinitely many solutions, well, then that would imply that the determinant of b has to be 0. Because if the determinant of b is non-zero, then b has an inverse, and bx equals 0 has a unique solution. So if we want not to have a unique solution, then b must not have an inverse, and therefore its determinant must be 0. So what that means for us, let's just put this off to the side here. What that means for us is that we really want this a minus lambda x quantity. There we go. So we really want this a minus lambda x quantity to have determinant 0. Okay. And let's think about that. What that means is that we want the determinant of a minus lambda I to be 0, and a minus lambda I is an n by n matrix, and we're just going to have to figure out what this is for generic matrices A. Okay, so this is going to be a pretty important equation for us. In fact, this is so important it has a name. This equation, so the equation, the determinant of a minus lambda I equals 0 is called the characteristic equation. So this is called the characteristic equation for the matrix A. And actually the left side the determinant of A minus lambda I, also has a name. Usually we write it as P of lambda. This is called the characteristic polynomial. So this is called the characteristic polynomial of A. And I want you to notice that if I think about this characteristic polynomial, so just notice that the characteristic polynomial is a polynomial. It's a polynomial with variable lambda of degree n. And so if we want to figure out solutions, and when this polynomial is equal to 0, we know that we'll have at most n solutions. So this tells us that A has at most n different eigenvalues. In the next video, we'll start to talk about some examples of eigenvalues and eigenvectors and eigenspaces of 2 by 2 matrices.